With this lesson, we'll be looking at the four basic gas laws. Those laws are going to be Boyles, Charles, Gay-Lussac's, and Avogadro. There are two more laws, which are combined gas law and ideal gas law, but we're going to save those for another video. For this one, we're just going to focus primarily on those four basic laws. Now, all the laws, no matter which one, study the effects of our four variables of gas. Those variables are pressure, temperature, volume, and moles, which is to say the amount of gas. So if you don't know what these variables are, we'll discuss those real quick. So a pressure is going to be how much force a gas exerts. As these gas molecules are in a container, they bounce around, they move around, and they collide with the surface of the container. And this causes a pressure. So we could say pressure, by our definition, is force exerted by those gas molecules on a surface area, and that surface area is the container they reside in. Now we measure our gas pressure in a couple different units of measure, but primarily you're going to see them measured in kilopascals or atmosphere. You might even see millimeters mercury, but the primary one being kilopascals and ATM for atmospheres. Now temperature, everybody should know what temperature is. That's how hot or cold something is. So as these gas molecules gain energy or lose energy, that affects their movement. So if you heat up a gas molecule, it moves around more, it bounces around more frequently, and it causes more collisions. Or vice versa, if you cool it down, then that molecule will slow down. There'll be less frequent collisions and bouncing around. So even though temperature is how hot or cold something is, we need a more scientific definition. So that's going to be the average kinetic energy of a gas molecule. So the average kinetic energy of a gas molecule. Now typically we measure things in Celsius and Fahrenheit, but with gas we need our temperatures to be in Kelvin. Need your temperatures to be in Kelvin. Next up we got volume. Volume is pretty much the amount of space available for something. So volume is going to be the amount of space available for gas molecules. And I am adding gas molecules to all these definitions because these variables are dealing with gas molecules. Like typically, the gas molecules may not be in those dictionary definitions, but for our purposes, I am adding gas molecules because that's what we're specifying here. And then lastly, we come to moles. If you remember moles from mole conversions or stoichiometry, this is pretty much the same thing. A mole is the amount of atoms of a substance, and this is no different. So moles of gas is going to be how much gas there is present, or the amount of atoms of that gas molecule is present. So moles is the amount of gas present. And moles are measured in moles. MOL. So that means if you have mass, you need to convert it to moles. Oh, almost forgot the measurements for volume. You'll see the measurements of volume to be liters, milliliters, you might even see centimeters cubed. Typically, you'll see it in liters though. So all four of these variables are going to be studied in our gas laws. Our four basic gas laws will hold two of these variables constant or unchanging, so we can then observe the effects of the other two variables on each other. So if I wanted to study how temperature affects pressure, I need to have volume and moles held constant. So as I increase or decrease the temperature, I can then observe what happens to the pressure. So our four gas laws are going to do exactly that. With Boyle's law, we study how pressure relates to volume. And Boyle's law says pressure has an inverse relationship with volume. Keyword there is inverse. Inverse means if one goes up, the other one goes down, or vice versa. So it's going to do the opposite. So if I were to take my pressure and increase pressure, volume will drop. Or if I decrease pressure, volume will go up. So to better help you visualize this pressure and volume changing and how they affect each other, I'm going to use a PHET simulation. If you've never used a PHET simulation, I highly recommend going to this website and using some for any of your chemistry lessons or physics lessons, whatever lessons you got. You can find them at phet.colorado.edu. They're highly educational. They're highly beneficial. So the one I'm going to be using is the gas property simulation. This is a simulation of how these variables affect each other. So I got variables of heat, pressure, volume, and particle amount. So with Boyle's law, I want to study pressure and how it relates to volume. So this gas chamber will be my volume. It has a width measurement here and a pressure gauge. These are two variables I want to study. So my temperature and my mole amount need to stay the same. So let's add one pump of gas molecules, and we put in 50 molecules. I want to keep my temperature at 300 Kelvin. So at 10 nanometers in this container, my pressure is hovering around 6 atmospheres. So as these molecules move about with their energy, they collide, they bounce, and they hit the sides of the container, and that causes a pressure. Now, if we change the size of this container, it should in turn change the pressure. So if pressure goes up, volume goes down. So that means if I were to decrease the size of this container, my pressure should go up. Or if I increase the size of this container, my pressure should go down. So let's just do a demonstration of that. Let's make this container smaller. Right now it's 10 nanometers. Let's make it 5 nanometers. Now I did change my temperature, so I'm going to cool that back down to 300 kelvins because I needed it to stay constant. Alright, so my temperature is back to constant. I have decreased the size of my container by roughly 1/2. So these molecules are more frequently hitting the sides of the container, causing the pressure to go up. Since I decreased the container by roughly 1/2, it increased my pressure by double. Now what would happen if we increase the size of that container by 50%? Originally we were at 10 nanometers, so let's take this thing out to 15. Give that gas a whole lot more room to bounce around. So now the gas molecules have more room. There's less instances of collisions with the container, and so our pressure has in turn gone down. So hopefully that visualization helps you understand it just a little bit better. Now with Boyle's law, it's a relationship between pressure and volume, and since there is a relationship, that means there is a mathematical formula. So our formula for this is the original pressure, I'll call it pressure 1, times its original volume, I'll call it volume 1, is set equal to the new pressure times the new volume. So all you gotta do is pick out your pressure and volume variables and plug into your formula, but make sure you keep your variables consistent. If it's the original pressure and volume, those go together. If it's the new pressure and volume, those values go together. Make sure you don't cross your values and put them in the wrong place. So let's look at a problem real quick. So we got a gas under 7 kilopascals of pressure in 5 liters. And it's compressed to 3.5 liters. What's the new pressure? Well, this can't be too bad. Let's pick out our variables. So first I see 7 kilopascals. That's a pressure. I know it's pressure because of kilopascals. And this 7 kilopascals is in 5 liters. That's another variable. That's volume. And that's 5 liters. I know it's a volume because of the liters. These two values go together. So I call this P1 and V1. We compress the volume to 3.5 liters. So I'm going to call this volume 2 since I compressed it. That's going to be 3.5 liters. Again, I know it's volume because of the liters, the liter sign. What is the new pressure? So I'm looking for this pressure 2. All right, there's our variables. Now let's write our formula, which is P1 times V1 equals P2 times V2, and then plug in our values. So P1 is 7, V1 is 5, P2 is X, and V2 is 3.5. Now we've got a little bit of algebra. 7 times 5 is 35. 3.5 times X is 3.5X. Divide by the value with X. That cancels. 35 divided by 3.5. X equals 10. Well, 10 what? Got to have a unit. Our pressure right now is in kilopascals. That's going to be 10 kPa. So our volume went down. Our pressure should have gone up, and it looks like it did, so we are probably good. Let's look at the next law. We got Charles' law. Charles' law studies how volume and temperature relate. So here, pressure and moles need to be a constant. So Charles' law looks at the relationship of temperature and volume, and it says temperature and volume have a direct relationship. So since it's direct, that means if temperature goes up, volume is going to go up. If temperature goes down, volume will go down. They do the same thing. Alright, so let's say we had a balloon. We're to stick this balloon in the freezer. So there's a bunch of ice in the freezer cooling it down. So all the energy of the molecules are going away into the ice of the freezer. So the temperature is going down. In time, that balloon, if you were to check on it again, would get smaller because those gas molecules aren't moving around as much. They're not hitting the sides of that balloon as much. So that balloon will get smaller in size than it originally was because it has lost that energy, so those molecules aren't pushing against the sides as much. Or on the flip side, if you were to heat that balloon up, that balloon would expand and get bigger. Now, just like the last law, since this is a relationship, or since this has a relationship, there's going to be a formula for it. So Charles' law formula is going to be the original volume divided by the original temperature is set equal to the new volume times the new temperature. So let's take that formula and work out a problem. So we got a gas with a temperature of 250 Kelvin. It occupies 3 liters of space. If you change the temperature to 400 Kelvin, what's the new volume? Let's pick out some information. We got 250 kelvins. That's temperature. And remember, it has to be in kelvins. So there's our temperature, and it occupies 3 liters of space. So this volume is 3 liters. Since these two variables go together, I'll call that temperature 1 and volume 1. We change the temperature to 400 kelvins. So it's a new temperature, so I'm going to call it temperature 2. That's 400 kelvins. What's the new volume? So what's this second volume here? So our formula is V over T. Is that equal to the new V over T? So now we just take these variables and plug it in. Volume 1 is 3 over 250. Volume 2 is X over 400. Cross multiply. 250 times X is 250X. 3 times 400 is 1200. Divide by the value with X. That cancels. 1200 divided by 250 gives us 4.8. 4.8. But 4.8 what? We're looking for volume, so this is going to be liters. Our temperature increased, so our volume should in turn increase as well, which it did, so we should be good. Alright, looking at the next law, which is Gay-Lussac's law. So Gay-Lussac looked at pressure and how it relates to temperature. And that law says pressure and temperature have a direct relationship. So just like Charles' law, this has a direct relationship. That means if one variable goes up, the other one goes up. So if I increase the pressure, that's because my temperature may have gone up. Or my pressure may have fallen because my temperature may have fallen. So we can use a PHET model for this one. So I'm going to increase the temperature. I'm going to throw in 50 molecules. So my 50 molecules at 300 Kelvin are at about 6 atmospheres. I'm going to keep the volume the same, and I'm just going to cool this thing down and see what happens to the pressure. So as our temperature drops, our pressure drops. We went from 6 atmospheres, now we're down to around 2. And the pressure dropped because look at these molecule movements. They're very slow. They're not moving too much. They're hardly hitting the sides now, so that pressure is not going to be a whole lot. So let's heat it up and see what happens. So as we heat up that temperature, those molecules gain more energy. They get more vigorous. They're moving around more. Since they're moving around more, they're hitting and colliding more, which causes the pressure of that container to go up. So we increase that temperature greatly, and the pressure hasn't increased greatly as a result, due to all this movement, due to all those collisions. So just like the last two laws, if there's a relationship, there is a formula. This one's just like Charles' law, and it's set up just different variables. So your original pressure will be over the original temperature, set equal to the new pressure over the new temperature. So let's look at a problem real quick. So if you cool down a gas at 2 atmospheres, 200 kelvins to 150 kelvins, what's the new pressure? So let's pick out some information. 2 atmospheres. Atmospheres is a pressure, and this pressure is at 200 kelvins. Kelvins is a temperature. We cool it down to 150, so that's another temperature. What's the new pressure? Since these two variables go together, I'm calling that P1 and T1. That makes this P2 and T2. And our formula was pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. Now take those variables and plug it in. So P1 is 2, temperature 1 is 200. V2 is X, and temperature 2 is 150. Cross multiply, 200 times X is 200X. 2 times 150 is 300. We divide by the value with X, that cancels out. 300 divided by 200 gives us 1.5. But 1.5 what? We're looking for pressure. Our pressure is currently in atmospheres. So this is ATM. There's our answer. Our temperature went down, so our pressure should have went down. And then we come to our last law, which is Avogadro's law. Avogadro, that name should be familiar to you if you know Avogadro's number. Avogadro dealt with the number of atoms. So his law deals with the number of atoms in the space they need. So that law says moles and volume have a direct relationship. Which should make sense to you. If you increase the number of molecules, you're going to have to increase the amount of space available for them. So, if your moles go up, your volume goes up. If your moles go down, your volume goes down. And since it's a relationship, there's a mathematical formula. And since it's a direct relationship, just like Charles and Lussac, it's going to look the same as those two laws. So your moles will be over your volume. That's your original moles and volume amounts that equal to your new moles and new volume amounts. So let's look at a little problem real quick. So if 4 moles of gas take up 750 liters, how much would that same gas take up if there's 9 moles? So let's pick out some information. I got 4 moles. 4 moles goes for moles. It takes up 750 milliliters. So my volume is 750 milliliters. Now, if I wanted to, I can change this to liters, or I can leave it milliliters since it's asking for the new volume. I just got to make sure I keep those units consistent. Since it's 4 moles of gas is at 750 milliliters, these two variables go together. That'll be N1 and V1. So we change the amount of gas to 9 moles. That's going to be N2. And we're looking for the new volume at which it takes up. So we're looking for V2. So our formula is N1 over V1, so that equals to N2 over V2. So let's just plug it in. So N1 is 4, V1 is 750, N2 is 9, and V2 is X. So we cross multiply. 4 times X is 4X. 9 times 750 is 6,750. We divide by the value with X, that cancels. So 6,750 divided by 4, it's going to be 1,687.5. And since we're dealing with milliliters, put it milliliters. So our moles went up, so the amount of space we needed should have gone up with it. So doing the 4 basic gas laws isn't too difficult. Things you got to keep in mind are these units. Remember your units for pressure. You'll see kilopascals and atmospheres. Your temperature has to be in kelvins, otherwise those formulas will not work. Temperature has to be in kelvins. Your volume will typically be in liters and milliliters, and your moles will be in moles. So those units help you identify which variable it is. And your formulas, just memorize them. Boyle's law is the only one that's really different. It's P times V equals P times V while the other three laws look similar. Right, Charles' law is V divided by T equals V divided by T, which is similar looking to Lussac's law, which is P divided by T equals P divided by T. Boyle's law is really the only one that's different. That one you multiply and divide. The other three you cross multiply and divide. Hopefully this video helps you understand gas laws a little bit better. And as always, good luck on your tests.